All right, so for today, this is what we'll attempt. So I won't make it full screen. So following on from what we didn't talk about last time, I guess, we'll kind of recap everything you need to know about multiphase flow, and then we'll talk individually about the movement of non-aqueous phase liquids in the subsurface by kind of taking everything that we know so far in terms of the theory of capillary behavior and permeability to say something about the movement of lighter and denser than water fluids, and to talk about the distributions of saturation in the subsurface and the implications for that for the thickness of these lenses that exist at the bottom at the capillary barriers. And we'll talk about methods of field sampling that hinge on that. So that's our plan for today. You've seen this before, but it's a useful figure. It really, actually, I'll do something else before I do that. It covers everything we've really talked about in this class so far. Perhaps this is a more useful one to think of first. And we started off with this top left figure early on and the one below it. And so we know that there's some architecture of non-aqueous fluids in the subsurface. This obviously is a DNAPL because it's gone below the water table. It leaves a smear or a chimney before it is arrested by a capillary barrier. If they're intermediate capillary barriers, it'll get hung up on those and fall off the sides in this kind of architecture of cascading trickles, I guess, down to the system. Wouldn't be a problem otherwise unless it dissolves, in which it carries the dissolved components downstream. We talked about this behavior in terms of our understanding in terms of capillary response. It matters what the size of the pores are, as exemplified here, I guess, in terms of large diameter pores, smaller diameter pores, small enough to halt the transport of this free phase red fluid, non-aqueous, non-wetting fluid. And only beyond this zone does it penetrate along the pathways that are most open. We could explain that in terms of the idea that we have capillaries that give a rise within them and control the immiscible flow of two fluids. It could be water and air. It could be water and a liquid, a non-aqueous liquid, a non-wetting liquid. And we could define some parameters about how high they would rise. We could define a parameter called capillary pressure, and we could define these capillary pressure versus saturation curves by doing an experiment in the lab. And so this is kind of summarized on this slide, which we looked at briefly last time. But it includes everything that we need to know. That the capillary pressure diagram, capillary pressure versus saturation diagram, and relative permeability diagrams sit on top of each other. They have common features in that they vary with saturation of water and saturation of non-wetting fluid, wetting fluid and non-wetting fluid. The wetting fluid is typically water. The non-wetting fluid could be air or the DNAPL. And the features on this figure say when this non-aqueous fluid starts to break into the porous medium called the bubbling pressure. We can define it in terms of function, which we call the Leverett function, where J is equal to capillary pressure over interfacial tension, permeability over porosity, square root, which we just plucked out of the air. We can define these irreducible saturations of water. The water we can't get out, the non-wetting fluid we can't get out, and those give us kind of no-go boundaries in both of these charts. We know that relative permeability is a way of defining the transmission of a non-wetting and a wetting fluid in the subsurface, and these are the capped terms that allow us to define those things. We know that if we want to, we can calculate the velocity or volumetric flow rate as Darcy's law, where Darcy's law we use kind of an effective permeability here and a pressure gradient. And we use this scaling parameter, which is a function of saturation, which we talked about drawing it as a function of these X curves, which perhaps weren't very satisfying because it doesn't drop off this irreducible saturation behavior. So we prefer maybe to use real curves, or if we did use X curves, we would use them that exclude these zones, right? So if we did use X curves, we'd use them something like this, which kind of represent these. Typically, we don't have very detailed information on this. It's a very expensive experiments to run, and we can do estimates usually without them. But these define these behaviors. We can also, as we did for fractures, define the permeability as you've used as a function of the aperture and the spacing between the individual fractures. We can also have a Capri model for the permeability of porous media as a function of the porosity, the diameter of the pores, and some coefficients. And actually we can use these two terms, which are evaluated here, in that Capri, the bubbling pressure, the pressure at which we get air entry into the system, or NAPL entry in the system, and we can link it to permeability, which might be useful to us, because they both, at a Capri level, involve the diameter of the pores. And so if we write each of these terms in terms of the diameter of the pores, for a single medium they're the same, so we can equate them to each other. And if we manipulate them, we end up getting an expression that is Capri pressure divided by the interfacial tension is equal to the square root of product times porosity. And that, of course, is our J function. And this, of course, is the number. We don't quite get 0.3, but this is where it comes from. The number that we have here is the number we got. And so the great importance for you, I guess, or for us in general, is that typically this is an unusual curve to measure. But if you know that this entry pressure is given by a Leverett function of 0.3, then it's quite easy to calculate what that is, because you'd like to know what this is. Often you know the permeability of a porous medium, often you know the porosity, and often you know or can get the interfacial tension. So immediately you can get this important parameter which defines when another fluid will start to invade it, and it's a useful design parameter for us to use. We talked about this in the context of those two figures that we had, an unsaturated figure on the left and a DNAPL figure on the right. These are the Capri pressure versus saturation curves. Whoops. I'm not sure what this is there for, but it is there. And these define something about how saturation changes in two circumstances. One from the water table up, which by definition the water table has atmospheric pressure. And as we go up, the Capri pressure is the difference between the water and the air pressure, which is essentially constant as we go up. And below the water table, if we have a non-wetting fluid in place, which is green and is denser than water, then the Capri pressure is just the difference between this non-wetting pressure and the wetting pressure. And so we can define exactly what the distribution of saturations are with depth, because we can always scale this in terms of the Capri pressure, which by definition, Capri pressure would be equal to elevation times gravity times density of the non-wetting fluid minus density of the wetting fluid, by definition. So if we know what this curve looks like in terms of Capri pressure, then we can always scale it if we know the densities and the planet we're on in terms of a depth. So that's the utility of maybe everything that we've done so far. So that's the recap so far. So what we'll do today is talk about, because we have that under our belt, we can talk about what the saturation behavior might be in a generic sense for NAPLs and water in the subsurface, and also how we might go about measuring those distributions of saturation. So things I don't talk about anymore because I don't think it's so relevant. But these figures, how many people, did anyone buy Federer's book? I'm guessing not. No, fine. No skin off my nose, as they'd say. So in these figures come from Federer. So in the vadose zone, this is our capillary pressure curve shown in height. It represents the fact that at the water table, this is atmospheric pressure, and as we carry up in the unsaturated pore space, then it will be atmospheric pressure all the way, because the density of air is only 1 kilogram per meter. It's essentially constant with height. But as you go up within the continuous water phase, I don't know, did we use red for water and green for air? So this would be capillary pressure. In the water, as we go up, this then is the capillary pressure, this difference between these two. And as you go up this curve, it's just the same as going up capillary pressure versus saturation curve. So what this physically means is that this portion here, if I switch out the colors, is water saturation. As would be this. And in the different zones below that, then this would be the saturation of the non-wetting fluid, which is air in this particular case. And of course you see that as you rise, it becomes more air saturated and less water saturated. We also know that in these zones we could imagine that if we had grains contacting each other, then the saturation on these grains would be pendular in this region here. So we talked about the donut that is the collar around the junction between two grains. It has two curvatures. In this one you see in the circumferential one, I guess, around its torus. And so in this particular case, the water would be present as a skin, a monomolecular skin on all these grains. In some respects it would be connected, but if you sucked fluid out of here, none of the water would come. You'd only get air out of the system. As opposed to in this lower zone, if I draw the same figure, the saturation is funicular, if I can draw it. I'm not going to do it. So the blue part, the saturating water, would again be these donut shapes, but they would enclose to basically, if I were to draw this out and enlarge it, I guess it would be something like a zone, a zone, a zone. I guess there's 4 there. So this would be saturation of the water, and this would all be water filled. And as you remember, funicular saturation is a bubble of air that sits in here. Now, if you suck fluid out of this, you'll get water out of it. You won't get air because it'll be stuck in the pore throat, and it won't be able to move. So we could expect to see these behaviors in these different proportions. So what we could do, if in the vadose zone, which everything that gets into the water table has to go down through the vadose zone if it's spilt from the surface, you could imagine a thought experiment or an actual experiment where you take a column in the lab which is 70 centimeters tall, less than a meter, less than 3 feet, and starts off with this tension saturated zone. So this is at atmospheric pressure here. This has not reached the bubbling pressure, so there's no air that's got into this system here. This in terms of water content, and so you'll remember that, not sure we said that saturation of water is equal to the volume of water over the volume of voids. Volumetric moisture content is equal to the volume of water over the total volume of the soil sample. And so here, if the water content is, what's this, 0.3, 0.4, this is 0.33. If this is fully saturated, then in this particular case, the porosity, which is all full of water, would be equal to 0.33. So just by definition. So it's the reference frame is just the void volume for saturation. When it's 100% saturated, then all of the open space within the porous medium is filled with water. But in this case, if all the pore space is filled with water, it's just filling the porosity, so this would be the value of the porosity. So just a different definition. So this is saturated in tension, so this is in tension. And then as you go up here, again, if we would draw this, this would be the saturation of water. I won't change colors. But this would be your saturation of the non-wetting fluid. Air, in other case. And so if you dump, this one first. So if you spill some oil into it, you'd expect that this would fill up from the surface. So if you drew, again, a profile across this, you can divide it into its components. So this would be water. Or I guess not saturation, it would be the moisture content, but let's think in terms of saturation. This would be saturation of the oil, and this would be saturation of air. So we have 3 fluids in the system. And we'd expect that as time goes on, this is just moving under the influence of gravity and permeability, but let's not worry about that. So the next time you have this, so now you have, if you draw a cross section across here, you have air, oil, and water, of course. And finally, when it comes to rest, you end up with something that looks like this. And if you extrapolate this to think about what we've talked about before, and I suppose drawing something across here, lower down, here, then by definition, if I just draw this, then this is the content that you have of oil. This is water. And this is air. And so if you draw a cartoon, I suppose, through this, you'd have something in terms of what we've kind of talked about before. Exactly what we've seen before. Water. So I guess I only drew part of that. This is this chimney. Do I not have red for that? Yes, I do. This is an artiste. And so this is the partially saturated chimney that we had before. And so it looks exactly what we talked about when we dealt with, I'll come back to this in 2 seconds, this behavior here. So this is exactly what we're trying to represent. And we're trying to rationalize exactly why we get that behavior and how it turns up in the records of what we now know about capillary pressure versus saturation curves. So this is a distribution of saturation with depth. Of course, it's the same as the capillary pressure versus saturation curves. We've written the behaviors in terms of moisture contents, which are related to each other through saturation. And we've defined exactly what these look like in terms of the saturation profiles. So this would be representing our puddle, if you like, the puddle that we have that exists at the bottom, which is nearly, not 100% saturated, but saturated except for a small amount of water and saturated except for a small amount of air that's present in the system as well. So if we also, so it looks like what we have. If we look at the same system, I think it's, well, perhaps it's not the same system, different heights. Yeah. If you look at a similar system and look instead of at the saturation distributions, but look at it in terms of pressures, then you have in terms of, I guess this is in a different sequence, same idea as before. So you start off with the water table. The water table by definition is where the pressure is atmospheric. Atmospheric is 0 centimeters of water gauge. So pressure is equal to density times gravity times elevation. And so by definition this would be Z0 in our system because the pressure is equal to Z0. Below it, it is the water table. Above it, it is partially saturated because it's tension saturated. The water's in tension. You know it's in tension because if we drew on it the air pressure here, the air pressure would go up like this, not quite on that axis, but this would be equivalent air pressure. Same as you feel as you go up in an airplane or up a building. So almost vertical. And so by definition, this would be the capillary pressure, PC, which defines the saturation. So now if you drop the oil from above, what happens is you start off with a water table, you drop the oil from above, and you change the pressures. All of a sudden you shift some of these pressures by saturating this zone here with this tongue of oil that we saw before. So it's not the same experiment, but it's exactly the same behavior. You have this tongue of oil coming down, which means that there's a pressure differential from 0 pressure here that would be rising within this oil, right, as you go down. So this would be the unit, the depth times the unit weight of oil as you go down. And so that's manifest by moving this curve to your right until it hits here. You keep on allowing it to go down. The tongue of oil compresses the water table and pushes it down from where it previously was. Compresses it. And then creates an oil table. And so this again looks like what we think we know we have. So by definition, from here on downwards is oil, gasoline, something that's lighter than water. From this point downwards, this is water that's fully saturated. And we have two tables, I guess. We have a water table, which is here. By definition, and we have an oil table. That both satisfy the definitions that at this point the pressure is atmospheric. Here it has atmosphere above it. Here it had atmosphere above it before, but now it's compressed, and this will be a zone which is gasoline and air in the system. And so that's physically what's happening in our system. So that also will look exactly, I'm not sure if I can draw it here. If I draw it in our same colors as before, this would be if it was in, it would be this. Actually, I'm going to move that down because it should be moved down, right? Actually, that's perfect. Yeah, sorry about that. So this now is the gasoline that's sitting on here. It should come up to this point here. Oh, no. I'm drawing it on the wrong diagram, right? So why don't I do this? That's exactly what it should look like. So this is gasoline on downwards. We're drawing green, red here, but it's green. So this is the lens that's sitting on top of it. Above us, we'd also have this zone of the chimney, which is up here, which is this. And physically, it's just exactly the same architecture as before, but now it's defined in terms of equivalent capillary pressures, which are defined on this axis here in terms of gauge pressures in centimeters of water, instead of being defined in terms of saturations or water pressures here. But you end up with exactly the same representation of what's going on. So all by way of explaining why we know this is the case. We know this is the case because the capillary pressure versus saturation curves allow us to scale between elevation in the aquifer and saturation. Won't talk about that. So here is the curious conundrum. So we saw from that we apparently had two tables, an oil table and a water table, right? Which was demonstrated by this. If you went down here and you measured the pressure at every single point, you find atmospheric pressure at the top of the oil, you find atmospheric pressure at the top of the water, and so that gives us a conundrum in terms of how we might measure the thickness of this lens of gasoline we have. So the question is, how do we get an accurate picture on exactly the thickness of that lens? And so the conundrum is that if we take this lens, was red before, but this is gasoline sitting on top of the water table. The only way you can find out what's going on in it is to drill a hole through it. If you drill a hole through it, the gasoline will flow into the well bore, and it will sit in that well bore to some depth. And the question is, how can you relate, is the depth that you measure in the well bore the same as the thickness of the puddle that sits on top of the water table? And the answer is no. And the reason that it's no is because you have two tables in this, water table and oil table. So by definition, in the oil, this point here is atmospheric pressure. By definition, in the water, this point here is atmospheric pressure. And so we can use those two pieces of information to figure out exactly what this height might be if we think it's going to be different from the true height in the aquifer. So this is what you measure if you go into the well bore. You'd measure a thickness of this stuff that is T in height, and you can measure that. But we'd like to take this and relate it to the actual height. So we know at this point here, if you look at that interface, the pressure acting downwards is going to be the pressure in the oil at this point. The pressure in the oil is going to be equal to the density of the oil times this height times gravity, this term here. And if it's sitting in equilibrium, not moving, then the pressure acting upwards has to be the same. And so the pressure acting upwards has to be equal to the density of the water. But because the water starts off at zero pressure here, then by the time it gets to this depth here, which is W, so this is atmospheric pressure. The pressure at this depth here is going to be the density times gravity times W. So this will be the pressure acting at this point, and that has to be acting up against this. So what we can do is we can just equate these two terms, nothing more. They have to be equal if it's not moving. If we equate them, we find out that the actual thickness of the product in the aquifer, the puddle, is equal to what we measure multiplied by the ratios of the densities. Nothing more than that. And so since the oil is floating, this will be less than the density of water. So this number is always less than 1. So if so the height of this puddle will always be less than the measured depth. So that's it. Perhaps you wouldn't expect that. Perhaps you'd expect to be able to measure exactly the same thing, but you can't. And the reason you can't is if it comes out with these two different water tables and oil tables. So why do we care about that? Well, we care about it because we might want to be able to calculate how much volume of fluid is in this lens here. And it's a pretty simple task for us to do that if we have this height. We have the equivalent height of this now as, I guess, W. I suppose we might know how areal extensive it is, which is area, perhaps. And if we do that, we can use what we know about our system to calculate the thickness. The thickness is just the measured thickness minus W. Yeah. W is that's not W. T minus W. This is T, this is W, hence this remaining part is T minus W. Then, yep.
Explain why the two heights become different. Is it because the two systems are disconnected in some way? Because I'm also not saying that they'd both be at atmospheric pressure.
Well, this clearly here is not at atmospheric pressure. So this is atmospheric pressure because it's got a continuous air path above it. So you're okay with that. This is atmospheric because by definition, the water table is where the pressure in that. So these are tables. This happens to be in oil. This happens to be in water. By definition, the water table is where the pressure is atmospheric. So what you have above here is a mixture that's compressed down, but it's retained this magnitude here. So what it's done is it's moved this saturation over to the right-hand side. So at these two locations, that is sitting under here, but by definition, there's some air in this space, and therefore it's been compressed and is left over and exists at atmospheric pressure. But in the bore,
Partly disconnected in that sense, I guess. Because I was thinking, like, if you put like oil on top of water, like that's going to apply some pressure to it. Like,
yes, yeah.
So they're disconnected by some depth of compressed air.
If it was oil directly over water,
Yeah,
then by directly this would be equal to rho G T minus W in our case, right? And this would have to be exactly the same at this point here. But yeah, they're disconnected because they have this layer between them.
Okay.
This pressure in here would have to be continuous,
Yeah.
and it would go down to this depth here, so that this term here would not be the same as this, right?
Yeah.
Good?
Okay, so that's how you get the different.
Yeah. They're disconnected between each other. They're not in contact.
Okay.
Okay. And you can see that because, I guess one of the point of doing this, because this goes up and it's got a dog's leg.
Yeah, because you increase pressure and then it just jumps back
Yeah.
over. So there's some.
So that's the reason. So if we want to calculate the volume that's present, then the thickness is going to be T minus W. The pore space is going to be the area times the thickness multiplied by the porosity. So this is pore space. And we know that within that pore space, if we look at what we've looked at before, these are the distributions of behavior. So this is the amount of water that's left. This is the oil table that we've just talked about. This is the water table. So this height here would be T minus W. And this is now essentially full of gasoline. And this is the irreducible saturation of water. And so, since this is 100% saturated, maybe, and this is 0% saturated, I guess they're written up here, then this S0 equals 1 minus SW0, right, by definition, brackets. So this whole length is 1, saturation of 1. If you subtract off the irreducible saturation of water, you're left with 1 minus SW0, and this is the amount here. So that is kind of the amount that you have in there. So this is the volume of the aquifer. This is the volume of the pore space. And this is the proportion of the pore space which is filled with NAPL, just by definition. And I suppose you could think that these actually have curves on them, so the saturation won't abruptly stop here. It would change into this portion of the chimney. But there's also be a saturation of the water that comes into here. So it's actually convenient for us just to be able to isolate this whole block, ignore these dashed lines here and here that almost compensate for each other, and just take this as the volume. So T minus W, areal extent A, gives the volume of the aquifer, multiplied by the pore space gives you how much space is in the pores, and then what the filling in this pores is given by this. So then the other part is how much of this can you actually remove? And so you'd think that in removing it, we have an irreducible saturation now. If the diagram's not getting too busy, we would have an irreducible saturation of the oil, 0, and that would be this amount here. So if you think about how much you can remove, and if you think about it, you're not going to be able to take out this portion because that's going to be the gasoline which is left stuck in the pore space, attached actually as funicular saturation. It'll be attached in the pore space. Where did we draw it? As a little bubble that's in the middle here that we can't get out of it. And so since we can't get that out, the only proportion that we can remove, gone too far, is going to be what we have in green. If I overprint this, green's a bad color. All we have in black. So the amount that can be removed is going to be the outline part in black. Right? So inside the black box is recoverable. And if you think about it, it makes sense. So we invade it with this green fluid. We can't get more in than the water allows. So there's some water left around the grains and at the grain contacts, and that's what this amount here is in this white box. So the amount of stuff we can get in is going to be this full amount given by the amount of saturation of oil. But when we want to take the oil out, we're going to be left with an amount of oil that's still going to be present within the system. So the amount that's recoverable is going to be the black box, which is here, which is just going to be exactly the expression we had before, this expression here, but with one extra term on it. Oh. It's a bit crazy. And the irreducible saturation of the non-wetting fluid is the amount that's in here that we're never going to be able to get out. We'll be able to get everything in the black box, but not this. And so it's a simple calculation to be able to do that. And probably as good a calculation as you have given the information you have of any particular site. I suppose you might not, well, actually let's do something else. Let's go back. If you have that down, so how do we do this in reality? Let's see if this will play. Let's have some light relief here.
Below the water table in soils and rock. The NAPL flute system is a simple and cost-effective technique for mapping NAPLs. We have developed a color-reactive cover for detection of pure products.
It's a sales
In
pitch.
one application, a compressed NAPL flute liner is inserted into push rods. Water is injected into the liner as
It's
the
not
rods are
playing?
pulled, causing the liner to dilate against the whole wall. This is a short description of the NAPL pure product developed by flexible liner stain.
Running in two places.
NAPL, the liner is inverted out to detect pure product, LNAPLs and DNAPLs above and below the water table in soils and rock.
Yeah, so.
The NAPL flute system is a simple and cost-effective technique for mapping NAPLs. We have developed a color-reactive cover for detection of pure product. In one application, a compressed NAPL flute liner is inserted into push rods. Water is injected into the liner as the rods are pulled, causing the liner to dilate against the whole wall. If there is pure product present, it will make a stain on the color-reactive liner. When the liner is inverted out of the hole, there it is, and laid out on the ground, you will be able to map the exact location and depth of the contamination with the tape measure. Here are the 5 simple steps
High tech, huh?
installing a NAPL flute color-reactive liner using
So-
the direct push method. Step 1, push the rods to depth. Step
2.
Install the NAPL flute liner and fill the annulus with water. This liner is going down very easily. Once the liner is in
So these are probes. You push a cone-shaped head down into the aquifer. Once you get down to the desired depth, you can push this liner down on the inside.
water is added to the annulus. We do this to keep the liner
Fill-
from dilating in the rod.
fill the
until
rods.
first rod section is pulled. Step 3, raise the rods one section and inject the water to dilate the liner in the hole.
So you pull the rods up, you leave the liner in the bottom, you inflate the liner so it's anchored to the bottom, and then you pull the rest of the rods up through the system.
Step
That's all you
4,
do.
Inject the water and then raise the rod. Repeat step 4 until all of the rods are removed. Injecting to fill the liner. Step 5.
So now you've got the whole system in, and so now you pull it from the inside out, so it, like a sausage skin, I guess. So it rises up inside but leaves the outside in contact, but turns in on itself, so that the stuff that was in contact, the wall that was in contact with the borehole and the NAPL in here, turns inside itself. I guess they show it quite well here.
Pull the tube to invert the liner from the hole. By inverting the liner out of the hole,
so you pull it from the bottom,
material from touching,
and so you're turning it inside out, basically like a sleeve. And they do some places. So pretty straightforward. So in other words, you can use some tools to be able to figure out exactly what you have in place. You can measure water levels by using, I don't know, steel tape, pretty straightforward. Electric tape, measuring water levels, not redevelopment. Yeah, none of this is very satisfying, I guess. Don't know if this one. Yeah. Well, measuring water levels in a well is just the same as dropping something down it to be able to measure it. But you can't measure, of course, you can measure the interface where you first hit fluid, but you can't necessarily measure the thickness of the free product which exists below that. And so the techniques that are used to do that, maybe this is a better one. No, these are both balers. So I thought one of these electric tape, yeah, perhaps this is better.
Hi, this
Hi.
video demonstrates methods for measuring water flow, the electric tape, a PDA for electronically recording measurements.
So a water well measurement is just by putting this, blah, blah. People don't use PDAs anymore, but they use
By
phones.
dipping the probe into tap water,
So all it is a two conductors on a tape that ends up in this little instrument here. The central pencil and the exterior portion are just conductors. They're joined when they're in water. A circuit's made, as you see here, and the two conductors are up either side of the tape. And so when you hit water, it makes a circuit, and a light goes on the little spool. And so you know from reading the measurement on the, I'm talking over myself, for the measurement on the tape, exactly what the depth of the water table is. And some of them you can use that will sense different fluids between upper and lower, but we've already seen how to do it with the reactive tape. And the other ways that you might want to measure depths would be by bailing the well. And bailing the well is also pretty straightforward. I guess we'll talk about this later. Bailer is just something that allows you to get a sample out of the well. Most of them are bottom entry bailers. It's just a plexiglass tube or a tube of something, usually plexiglass, that's open at the top, but also open at the bottom with a check valve. You put down the hole so it fills like a bucket in a well, and you pull it out, the sample. You may get some reading of what the depth of the product is just by doing this. And I guess the one important thing to note maybe is that how these bailers work is that they're usually bottom loading. And so I think in this case he's going to show you exactly how it works. Yeah, working principle. You can see it. So it's on a string to go down the hole. This has a ball valve on it only. So it's just a floating ball that sits on a seat. The ball's buoyant, so when it goes down in the water, the ball floats up and allows fluid into the sampler. When you pull up and there's the weight of the fluid in the tube is big enough to close the check valve, and it allows you to pull the sample up. And so that allows you to get a sample from water. So really pretty straightforward stuff, but perhaps important to understand the practicalities of it. So, and the reason for doing that is that we want to be able to figure out exactly what this measured height in the borehole is, and to be able to calculate exactly what the amount of component we might have in the system. The more complicated way we could do this, which we won't, is to realize that when we look at this, these are the curves on the capillary pressure versus saturation curves that we have for water and oil and air and oil, which you could imagine we would have. What we've done is we've ignored these and assumed that maybe this area here is the same as this area here, so they balance out, and we can just take this aggregate height. If we wanted to be really fancy about this, what we could do is we could take our capillary pressure curves, which are defining this exact behavior. And I can't draw these very well, but you get the picture. This is capillary pressure versus saturation. And you might remember that we converted these into Brooks-Corey curves. And you remember that we converted these by using effective saturation into something that we could write as log capillary pressure versus log effective saturation. And the curves all of a sudden were straight lines. And so this curve, if we translated the capillary pressure versus saturation into an effective saturation, which just excluded some of the pore space, we could convert this squirrely curve into a straight line. Why did we do that? Well, one reason we might want to have done that is because now we can use these straight lines to represent this very behavior here quite straightforwardly in a mathematical sense. And so if we wanted to, we could use these modified capillary pressure curves to come with a much more complicated version of saturation versus depth, which would look like this. This is exactly the same curve we've looked at before. So this is a borehole. This is the free product in the borehole, what we've called T before, right? This height. And we have this more complicated behavior that we can represent, that we had these portions. So this portion here would be the irreducible saturation of water. This would be the saturation of oil within our system. And as we wanted to remove it, the amount of residual oil that would be left would be this amount here. The irreducible saturation of the oil. So this is exactly the same as the figure we saw before on this figure here, right? Just drawn out in schematic. And what Feder does, or reports in his book, is how you could use these representations of the capillary pressure versus saturation curves to much more accurately get an idea of the distribution of saturation in this zone. That's all. And to calculate exactly what the recoverable product would be. And I don't intend to go through these 85 equations. You get them if you want. Perfectly adequate for us to be able to use this. Block it off. The total region here is the amount of oil that goes into the system. Multiply it by area times height and the pore space that's available. If you want to get rid of this, the only amount you can get rid of is this amount up to this point here, and you're always left with this. And that's going to be good enough for us in this class. Okay, what else? Okay, I guess another practical idea, another simple idea to get your head around is that what happens if the water table isn't static? So we've made the point that we have this chimney that comes down, with this partially saturated oil, perhaps this 10% or 20% saturated in oil in this chimney, and then it lies on top of the water table as this puddle, which is nearly 100% saturated. We know exactly what it looks like if we draw a section through it. In this zone, it's mainly air. So we're looking at in this zone here. So most of it is air. There's a smear of oil. And there's the residual water that's present because it's partially saturated already. All of this is partially saturated. And as we come down to this zone here, by definition, we're essentially almost 100%. No, sorry, this is, that's not right. Get rid of this. In this zone here, we're 100% water saturated. And in this region here, this is our lens of oil. If I move that up here, this is the maximum saturation we have, not very big in this particular case, and the rest is water. And so the only point in noting this is that since this spreads out across the free surface, if you drop oil in a swimming pool, it spreads out to a monomolecular layer. This doesn't spread that far because it's got some weight to it and therefore is depressed and has a volume and a height to it. But if the water table now drops, so if you have a drought or a seasonal change in the water table and the water table goes down, then what it would do is it would take this distribution of this lens and drag it down through the system. So in other words, in here, it would just merely smear this in the same way that it smeared this as it went down. Except now it's smearing it through what was water saturated, not air saturated. So now you have this zone here, which instead of just being this column here, is spread out. And so that now, if the water table rebounds, and so if this water table rebounds and goes to this, you have this kind of anomalous situation that you have residual oil that's present in the chimney, but is also present below it. And if you drew a diagram of exactly what that would look like, then you'd have within this system, you'd have residual oil below here, gasoline, and you'd have this was essentially water filled up here. And so I guess the point being that even if you're discharging something that's lighter than water, it can get below the water table, but only by doing something like this, if it's carried down by the seasonal migration of the water table with depth. Oh, we're running out of time. So, talk about DNAPLs. Yes, you should shout, by the way.
What?
You should shout if I don't see you.
Oh. In this case, when the water table drops, are we assuming that just the oil smears and no air infiltrates?
It's completely capped by oil here, almost to the exclusion of air. So only oil will go down here and smear. I guess air would go down here. In this portion, air would go down, right?
Yeah, because I think on the second graph there, like as the water table drops, it looks like you see how you have oil saturation, but you also have some air. It looks like too.
So this would be air, and this would be oil plus air.
I guess there is air in here.
Yeah, I guess, but this, if you draw a direct line down from here, I guess this is also kind of showing, and I think they mean to show this, that this would have been the location of that, but it's the tongue is spread out more on the surface because it's down, flowing down gradient.
The
So
reason I was asking that was because on the third graph,
Yeah, there may be residual air in there. I don't think you can show it. Yeah. Maybe residual air, since you had air before. Okay. Yeah, good with that. All right. So, what about DNAPLs? Again, I won't go through all this verbiage. We can look exactly at what we'd expect to see. And I guess the first point relates to what we talked about. If these are wells, this is denser than water. So within a well, it would sink to the bottom, and the water would float on the top. These would be exactly the same figures as before. As you go down in depth, this would be if you go across here. Then the largest portion of this is DNAPL. The smallest portion of this is water. Again, there's no coincidence this looks like the capillary pressure versus saturation curve. But I guess what this figure is making the point as if this was a capillary barrier. Is that my stuff playing in the background? Or is it someone next door? Fine. It is next door. Is that if this was a capillary barrier, in other words, if the bubbling pressure was too high to be able to have the fluids go across it, low permeability, small pore spaces, then nothing would go across here, and that's fine. But if you drill a well which goes through this, then there actually won't be anything in here. But what will happen is the stuff that's in the borehole or in the aquifer above this will just fall into the well and fill it to an apparent depth. So I guess you might say that this is a phantom depth that doesn't exist. So if you're calculating the depth of free product, the depth would be from the surface down to the capillary barrier. The reservoir, the aquifer, would empty out by flowing into the borehole if the borehole was deeper. But of course, this part of the aquifer would not be filled with DNAPL. And so if you thought in your baler or in your measurement with the fluid system that it went down to the full depth of your borehole, you'd be wrong, right? And so you'd be overestimating the amount that's present within the system. So just to, again, to suggest how we might be careful. And finally, looking at DNAPLs, you'll remember that we looked at, if I draw these up high, we need better soundproofing here, or perhaps I need to talk louder. They must be playing a movie. It sounds different when you listen to someone speaking versus listen to something that's a movie. So you remember the saturation of water. We talked about capillary pressure curves in terms of this. So this is just turned upside down. So this would represent something which is a permeability which is high, and this would be a permeability which is low, right? The entry pressures of this are high entry pressures, which have to overcome the very small pore spaces which are present in low permeability materials. And so these two systems represent here low porosity, but actually really probably it's low permeability, and it's high porosity. And so these also say something about the distributions of the fluids in the subsurface. So if we look for the the high permeability system, which is this one, if we draw it upside down, then we'd expect that all of a sudden, if you increase the capillary pressure a small amount, you invade a lot of the pore space with this non-aqueous fluid. So it means that with water here, you can get NAPL invading quite easily. And so in this, I guess if you choose this spot here, this would be water, and this would be DNAPL. And therefore, at a very shallow depth, you've already reached a very high saturation of DNAPL because it can get in there very easily. It's kind of intuitive, I suppose. If you have a high permeability, large pore spaces, it can invade very easily, and it doesn't take a very high capillary pressure to be able to fill the pore space, and you get a higher up in the section, you have a capillary pressure large enough that it can invade all of the pore space. But if you have a low permeability, if you're working on this curve, it takes a much higher bubbling pressure to get into the system in the first place. And so in the upper regions, you'd expect more of it to be water-filled and partially water and NAPL, and only at deeper depths would it be NAPL-filled. So if you look at this elevation here, this happens to be, actually this happens to be water still, and this happens to be DNAPL. So merely by thinking about what these capillary pressure versus saturation curves look like as we measure them, inverting them to be able to look at them not in terms of capillary pressure, but this would also be increasing depth. So this would be Z equals 0, Z equals big as you go down in depth. So capillary pressure increases with depth because we know that capillary pressure equals Z times G times rho DNAPL minus rho water. So this is probably 1,600 kilograms per cubic meter. This is 1,000, as you know. So it's denser than water, hence it sinks. And so we can say, absolutely rationalize exactly why the distributions of these systems should be the same. So this one with low permeability would only have, at very high capillary pressures, very high depths, be fully saturated. So this would be, in terms of what we drew before, this would be our puddle of NAPL, and this would be our puddle of NAPL in this particular case. Different thicknesses. And we can rationalize it again based on this, which is what we did before, I suppose. It's no different from what we did on and on right here. These are exactly the same diagrams. Again, two fluids, one wetting, water in both cases, and one non-wetting, DNAPL and LNAPL in the other cases. Okay. So I don't know, I know I'm probably giving you whiplash, that's fine. So that's almost the parting shot. We've looked at this already. You can imagine that if you have a borehole and you drill that borehole, that the lighter than water fluid will float on the top, and so but a denser than water fluid will sink to the bottom. If you want to sample them, you have to, if you want the denser than water fluid, you have to go right to the bottom of the borehole, and that's why you have bottom entry bailers, which allow you to sample the fluid from the very termination, I guess, of the borehole. Whereas if you have a tube that is just weighted, that doesn't have a ball valve on the bottom, you could drop it low enough in here to allow the sampling fluid to come over the top. You can't necessarily do that if your fluid immediately floats to the bottom. And so you have to be mindful of that. Talked about that. I think that's the end. So yeah, I don't want to talk about those things. The other thing is you can imagine that if you're doing site investigation and you drill boreholes down through this, these will tend to be very unpredictable in terms of where the components might go, and drilling a well bore in this might mean that you don't find anything when it's really there. If you don't have the right intersections with fractures that can flow into the borehole and allow you to sample the stuff that's in the subsurface. So, yeah, okay. So that's all we'll talk about non-aqueous phase liquids. Next time we'll talk about the tension saturated zone. Again, 2 different fluids in place. And this is week 4, so homework 3, I guess, is due on Thursday. Okay, great. Thank you.